12 years to do that. It takes that much time to put a critical application, critical component into that service, which is made through additive manufacturing. See, let us see why qualification is very important. See, suppose in our house, we got a recipe, every details are there. I wanted to make recipe out of some food, right? Whatever the food I make, it will not taste as good as what my grandma makes, right? Why? Even though everything is there, but why food taste only differs? What is the difference in this entire chain? Raw material, everything same. But why the taste is different, output is different? Only difference is your grandma only. Grandma knows what to do, when to mix, what quantity, what level, everything she knows. That know-how she has it, that we don't have. Okay, the same analogy, it holds good for our 3D printing application. We have all industry standards are there, specifications are, everything is there. There are two companies, two engineers. See, same part, same thing. Both the things will have different quality. Because the way he build the part, the way other person builds the part, totally both are different. Okay, that difference comes because of manufacturing know-how. How we are going to, because there are so many variations. I can build a part in a 3D printing machine, single part I can put it in multiple orientation. What kind of scan strategy I am following, that is different thing. What kind of support structure I am planning, everything matters. It affects your final quality. Okay, this know-how is very important. That's why the qualification things are, whenever they are doing qualifying, each and every step is controlled in additive manufacturing so that you get a repeatable part. See, what is that qualification things are? These four things are focused. Stability of the process, capability of the process, repeatability, and reproducibility. These four things to be controlled. Once you control, you can go for, successfully you can produce a part in any numbers. Next, we got in DRDL, we got one metal machine which has got a size of 275 270 build volume size of 275 270 and 420 mm. We can make up to 250 by 250, maximum of 380 mm height part we can make. We made some of the parts almost. Some of the parts I could not show some engine component because of this some restriction. But we made a lot of internal components. We tested, successfully tested. Some air bottles we made it. See, this is the one large area application. DRDL is now making steps toward the baby steps toward the large area additive manufacturing. This is one of the biggest part we ever made, even biggest ever part made in through LPBF process in the country. Because we realized this component is one of the engine panel, scramjet engine panel. Through Agnikul, our private industry partner, through Agnikul, we realized that almost 630 mm width is there. Once it is these two, and see that what are the issues are coming up when you scale up that bigger components to study that we print it. Maybe another 1 or 2 years, DRDO will make the completely with a full scale scramjet engine will come up with the entirely on 3D printing. Because the problem is when you scale it up, there are issues are there. It's not so simple. Even my machine, if I want to load almost full height of 400 mm height, if I want to load, I need a half a ton of metal powder. If I say Inconel 718, I need a half a ton of metal powder. In this case, suppose this machine is around 450 by 450, almost 1 meter height, that Agnikul machine, it takes nearly 2 tons of powder. DRDL is planning to make almost 800 by 800 and 1500 height component we want to build as a monolithic part engine that requires minimum 8 to 10 tons of powder, metal powder. Now in the country today, no supplier can supply that 8 to 10 tons except Indo-MM capacity also. In one melt you can maximum you can go for especially for LPBF when you make, even he makes 200 kg. Out of 200 kg you'll get only maybe 160 or 170 kg for yield for LPBF application, because that is the issue is there. Powder, if I am going for large area, the powder, I need a bigger engine, even 1.5 meter if I go, I need 8 to 9 tons of powder for one build. Even though I will reuse it, but To build that, I start with 8 tons of powder and handling the powder. These are the issues are there. Currently, in the country, powder making things should be scaled up. That is another issue. See, the qualification approach adopted by DRDL. These are approach. Basically, we qualify from input material, machine parameters, process environment. We'll monitor that moisture, oxygen content, everything. Institute part monitoring. We got an online part monitoring features also there in our machine, and inspection testing, post processing, and qualification. This is a thing we'll follow in DRDL. See, this we have got so many process control documents are there. See, infrastructure, how to, these are so many, almost nearly we got 20-25 documents are there to ensure that aerospace quality. So many documents to be ensured. Each and every steps to be repeated. If some new operator comes, he should be able to, by seeing the document, he should be able to repeat the process. Because in additive, as per ASTM standard, training the operator is mandatory. They are very clearly says, standard says that you have to conduct, any certification agency has to conduct exams. Okay, that after passing that minimum mark only, they have to give a certified operator only to be used. That way their standards are specifying the requirement. See, majorly this ASTM specifies that there are qualification part into 3. One is installation qualification, operational qualification, performance qualification. The installation qualification, basically you see right side of the card, test certificate. Basically, when the machine is getting installed, the manufacturer has to prove that it is as per the OEM specification, machine is working. That can be done using a test certificate. Then, once the machine, the operation qualification, you have to entire process map within that process variable, what is the capability of the machine to be built. Performance qualification is basically actual part, when you are building actual part. That also be not only actual part when you are building not only one part, for different batch to batch material or different printers also you have to qualify if you have multiple printers. That to be there. In addition, we are using that melt pool monitoring system. Basically, it takes the in-situ monitoring features also there. See, what are the challenges we are facing in qualification? One is process variability and repeatability, material and powder qualification, defect detection. Because majorly when you go for NDT techniques, the defect detection is a major problem because it is because additive manufacturing you will get a monolithic structure, defect detection. Majority we are having smaller part, we are going with the CT. We are doing that. But CT also has got some minimum size. But the problem is when you go for monolithic structure, bigger size part, existing in the country we don't have a CT, bigger machines. That is another issue is there. Another, material property variability, lack of standardized qualification framework, post-processing requirement, inspection, testing complexity. Let us see this. What are the challenges? You see, let us assume that in a single build, I am building so many parts in a single build. The part at first one and part at 10th part will have the same property? No, definitely it's not. Definitely vary. Especially this, I am especially talking with respect to LPBF application, right? If I build 100 components in my build plate, same geometry, part 1 and part 2 part 10 will have definitely will have variation in property. Okay. Similarly, it is a single build within a one build. Suppose build to build, first build I am making, second build in the same machine, same part, first build and second build will have the same property. Definitely, some variation will be there. But the qualification requirement is it should not random. It should not be random. At least it should be consistency. Consistency should be there. Part 1 to part 10. Suppose if I am having the variation of less than 10% or 20 MP variation, if it is consistent, that is acceptable. But randomly it should not vary. That is another requirement. What are the changes? Another thing, basically, one problem with that qualification, suppose if I established the process, I build it. I want to change small modification. I introduce some sharp fillet radius or some build file I want to change it. Entire qualification things I have to repeat it. That is a major challenge for us. There are stray vectors and critical process changes, design changes, feedstock variability. Suppose I have purchased one vendor, tomorrow I am getting from another source, that to be qualified. Multi-layer system. Another peril is whatever the machine we are having on single layer system. If I go with a multiple layer system, the multiple layer system interaction and calibration is the biggest headache, and stitching, some more stitching issues also there. That portion also qualification is bigger issues are there. Now, that America, ANSI and America makes, once in 2 years, they are trying to identify the gap between the standardization and certification gap. This year in 2025, recently they released it. This group has categorized what are the gaps are in certification, model-based material and process definition. That's just I copied from that document what are things are. Basically, these experimental identified variables are key process parameter variables and uncertainty qualification standards, process machine equivalence and testing standards. Okay, and again, digital engineering, digital thread, because what they want thing is now maintaining, because we are when you are making a number of parts, you are maintaining the entire digital thread is very important. That standards also not well. People are storing on their own things. Every industry is following their own standard, but that has to be standardized. Another one, coupon to part performance evaluation. How, suppose I am doing whenever I am making a part, I am making coupon. But coupon to part, how to connect it? That is not, that gap is there. Whatever we are doing now, functional qualification only we are doing. We are building a full part. If required, we are destroying we are making 1 or 2 parts, we are completely destroying the part, then we are evaluating. But that is not so. We wanted to go coupon to part evaluation also to be done. Model informed test locations. These are the things they are. See, certification. See, for production to happen, qualification and certification, both the things should be completed, then only you can go for production. That is a requirement for production of any component aerospace system. Now, one case study, because this I taken from Eton, the jet pump, basically made of aluminum ALSA 10 mg, they reduced almost single piece they made it, 11 plus component single piece, almost 40% lead time reduction. What the process thing they followed? See, one is material and machine qualification and product development. Once the material, everything qualified, then they built the part. They modified the design. Once the design is modified for additive manufacturing, see, what we are doing is, we are taking the part which is designed for conventional application, we are directly taking it in printer and doing that. That is not so. You will not get a real benefit out of it. You have to design a part for suiting to additive manufacturing requirement, then you will get all the benefit of additive manufacturing. They will design a part for meeting the additive manufacturing requirement. Then similarly, for any new design, they will do PDR, CDR, all those things are done, and product qualification. And